So my name is Flavio Ponzina. I'm a PhD student at the Embedded Systems Laboratory of EPFL, and I'm now going to present you a new paper on overflow-free compute memories for AGI acceleration. I will start with a brief introduction, showing you the context and the main challenge that we address in this paper. And then I will present you our hardware-software co-design methodology to avoid overflows in compute memories. I will show you the achieved results and finally conclude this presentation. So we know that the main challenge in the field of AGI is to execute compute-intense models like convolutional neural networks or CNNs into constrained devices. Now, focusing on CNNs, we know that these are layer-based architectures where convolutional and fully connected layers account for the largest fraction of memory and computing requirements. This is also visible with this plot that shows that to achieve very high accuracy, we need more and more complex models. And that's why we need optimization in this field. One way to address this challenge is by considering processing in memory solutions, where you add few logic at the periphery of memory elements, and this allows you to bring computation directly where data resides, reducing the number of data movements and allowing for a high degree of computing parallelism. When designing processing in memory solutions, you may have different choices. So you can focus on different memory technology, bringing computation in the digital or in the analog domain, and integrating the system as an in-memory computing or as a near-memory computing solution. But in all cases, we have a problem. And the problem here is that we need to perform computation using fixed bit width values. That means that we are prone to numerical overflows that can affect the quality of our output. So that's the main challenge that we address in this paper. We propose an hardware software co-design strategy to prevent overflows by constructions in compute memories. And in particular, we propose a solution which the compute memory is designed both as a near memory and as a near memory computing alternative. And we also present an hardware-aware optimization of CNN models. Now, this is a co-design methodology, and we've seen in the keynote this morning that a co-design approach is key, it's very important. And in fact, this allows us to achieve high performance and efficiency. We combine different elements, so I will tell you something about the scaling of input and output operands to prevent overflows, a corresponding hardware design based on compute memories, and a quantization strategy to improve performance and efficiency. Then I will combine all these elements together in a co-design approach to propose an overall acceleration workflow using compute memories. Going back to the previous slide, I'm highlighting here in blue the design choice in this paper. So we consider SRAM memories, computation in the digital domain, and as I said, both in-memory computing and near-memory solutions are viable alternatives, so we consider both in this paper. So let me start with analyzing the individual elements of this strategy. And I will start with the acceleration of AGI workloads. So we know, even if we focus on CNNs, that convolutional and fully connected layers, for example, account for the big part of computation in these workloads. So we want to accelerate these layers. And in the end, they can be decomposed into dot products. So this is the basic operation that we need to accelerate in the compute memory. You see, we have a series of multiplications and additions. Focusing on multiplications, you see here an example where we have two input operands, one named IMO, which stands for in-memory operands, and the other BO, as you can see in the picture, named broadcaster operands. Why? Because one of the two is actually stored inside the memory array, the in-memory operand, while the other is streamed from outside, directly inside the logic of the compute memory. Focusing on multiplication, here you see the multiplication algorithm that we employ. So you see different instructions that we need to execute. It's an iterative algorithm. And I highlighted with the different colors the basic operation that we need to implement in the logic. So you see we need additions, right shift, and negations to compute the two's complement. But what is important to notice here is that the number of instructions correspond to the number of clock cycles that we need to implement each multiplication, and it's linearly related to the number of bits, and in particular to the number of ones in the broadcaster operand. And that's a key observation. I will go back to this when I will discuss CNN optimization. But for the moment, let's focus on overflows. So when we have overflows, well, in general, we have overflows every time that the data range increases. So let's now analyze data range in the dot products that we need to accelerate in the compute memory. Consider that we use quantized data using fixed point notation with n integer bits and m decimal bits. So when we actually have to execute multiplications, our proposal is to pre-scale both input operands. As you see, we have in-memory operands between 0 and 1, so we only need mx decimal bits, while broadcaster operands are between -1 and 1, so we need 1 bit at least for the sign in this case, and we use in general y bits for the decimal parts. Notice that the computed products will be stored inside the memory array, so they must have the same bit width of the in-memory operand. Now, each product by construction will be again between -1 and 1. Why? Because we are multiplying two numbers, one between 0 and 1, and the other between -1 and 1. So we need to use 1 bit for the sign, and we use the remaining x minus 1 bit to represent the decimal part. But again, what is important is that in this case, the data range is not increasing, so we don't have overflows by construction if we apply this pre-scaling technique. Now, the picture is different when we consider accumulation. Why? Because in this case, we have individual products which must be accumulated, in general, n times. And again, each of them is between -1 and 1, but they can increase the data range of the output. So in this case, we have a number of integer bits required to represent the output, which grows logarithmically with the number n of accumulation, which is a good thing because it means that it's not exploding with the number of accumulation, but still it means that it's increasing. The data range increases. So we have overflows. And our solution in this case is to manage overflows, this type of overflows, directly in hardware. So as I said, we consider SRAM as the compute memory in this paper. You see, we have multiple SRAM arrays connected with an H3 interconnection to achieve high clock frequency and high degree of computing parallelism. And we consider a near memory computing solution as well as an in-memory computing solution. Now, the near memory computing solution, the design is slightly more simpler, I would say, because the SRAM is an SRAM. So you can take the IP of that memory and just add some logic in the periphery of the memory to implement the logic that it's required to perform your computation. Conversely, the in-memory computing design is slightly more complex because you need to manipulate the memory. You need to change the structure of the memory to perform computation directly inside the memory. We exploit the concept of bitline computing, but the additional effort that you need to put here to design this solution allows you in the end to achieve smaller area and better energy efficiency. Now, I will describe first the near memory computing design that we propose. You see, we have the SRAM array and the peripheral logic that accelerate the products and prevent overflows. This is the more detailed view. Now, going back, starting from the top left, we have one register to store one operand, which is the in-memory operand. While, as I said, broadcaster operands are streamed from outside, and in this case, they are used to control this multiplexer that determines the type of operation that we need to implement at each step. We also need one register to store the individual products and another one to store the accumulations. Notice that the MAC register is a 32-bit register. And that's our solution to prevent overflows in accumulations, because we can leverage the 16 additional bits to prevent overflows by construction up to a number n of accumulations, which by definition is equal to 2 to the 16, which is a really high number. We also need to implement addition, right shift, and negations to perform the multiplication algorithm I showed you before. And notice that this design, this circuit is not the all overhead you have to implement our solution. You still have to design your logic as a compute memory. So the actual overhead here to prevent overflows is the only part that I highlighted in yellow. Now let's move to the in-memory computing solution. In this case, it's more complex. So we'll just focus on the details of a single bit column. So you see the structure is similar to what you've seen before, at least with these colors. But again, the key here to prevent overflows is the multiply accumulate registers. So here you see a more detailed view, but again, you see there is a register to store the individual product and another one to store the accumulations. Notice that now the MAC register is split into MAC-L and MAC-H. So we actually perform accumulations in MAC-L, but every time that there is an overflow, we actually increase by 1 or -1. I mean, it depends on positive or negative overflows. the MAC-H register. So that's an overflow register, basically. And that can be efficiently done if we also store, as we do, some additional constants which store the values -1 and 1. Again, we have the circuit for addition, that's the circuit for redshift, and this is for retrieving the negation of the bit cell. In this case, the overhead to implement the overflow-free part of this design is even smaller than what I showed you before. So at this point, I've shown you how to manage overflows by scaling and by properly designed compute memories. But is there something more we can do at the application level? The answer is yes. We can optimize quantization in CNN to improve performance, leveraging the capabilities of the design compute memory. So what we propose is a per-layer quantization strategy that follows a greedy approach. So what we do is actually, at each step, we evaluate the impact on the number of clock cycles of quantizing more aggressively in-memory operands or broadcaster operands in each layer of the model. And what we do is simply applying the approach that maximizes the reduction in clock cycle. So we apply that, and we retrain the model for few retraining epochs to compensate for any accuracy drop. And we check accuracy. We check accuracy, but we also compare the obtained accuracy with a user-defined accuracy threshold. So if we meet the user-defined constraint, we just repeat the loop, trying to maximize quantization. Otherwise, before repeating the loop, we discard this optimization step, and we are not going to consider it anymore in future iterations. Notice that this is an hardware-aware quantization strategy. Why? Because, as I said before, broadcaster operands are streamed from outside, directly inside the logic, but 1 bit at a time. That means that every bit width reduction will correspond to a reduction in the number of clock cycles. So in this case, we can quantize broadcaster operands with any bit width level, because any bit width reduction corresponds to a reduction in the runtime. But in-memory operands are actually stored inside the memory array. So they can either be on 16-bit, which is the bit width of the memory word, or on 8-bit, because the architecture also supports word-level parallelism. Now, we also combine all these 3 elements together to propose an overall acceleration workflow for CNNs in compute memory. We know that we need to scale data when doing that. So that's what we do. The first thing is actually taking input activations and scaling them so that we ensure these in-memory operands are between 0 and 1. Similarly for the weights, between -1 and 1 in this case, but this operation can be done offline because weights are static data. Then we actually store in-memory operands inside the compute memory, and we stream weights to compute these operations. So we have in this example convolution, but we also have fully connected layers, in general dot products. So we use these to perform multiplications and dot products. These dot products are actually computed using pre-scaling input activations. So we need to scale them back to retrieve the expected output. As you see, we are actually combining scaling technique with the design overflow-free compute memory and optimized weights in this case. So let me now show you the results. You see, here I'm going to show you different experiments to evaluate the different aspects of this methodology. So I will focus on the hardware design, of the evaluation of the quantization strategy, as well as the overall comparison with state of the art. Now, let me start with the hardware design. We consider 6 transistors SRAMs built on a TSMC 28 nanometers technology. We support word-level parallelism, and we have multiple subarrays of 2 kilobytes. The frequency can be set up to 2.2 gigahertz. So let's now compare the 2 alternatives. Here you see the comparison in terms of area. And as expected, most of the area is dominated by the memory itself, while the in-memory computing solution is slightly more compact than the near-memory computing alternative. Notice that in this case, again, the overhead that we need to implement an overflow-free compute memory is limited. It's not the whole processing element, but it's limited to less than 5% in this case. This is the energy analysis. You see the energy consumption of the memory as well as the energy consumption of the 2 different processing elements. And we measure 60% less energy efficiency for IMC. So again, IMC is more complex to design, but it allows you to achieve a more compact and a more energy efficient solution. Let me now present the evaluation of the quantization. We have a PyTorch-based environment to train and optimize the models, and these are the benchmarks that we considered in this work. So as a baseline for comparison, we have a uniformly quantized CNN using 8-bit IMO, 8-bit BOs and 16-bit IMOs, because this quantization level has no accuracy degradation with respect to floating point mode. We also set the accuracy threshold to 1%. And that's what we obtained. So for SNET-A, but these results extend to different benchmarks. So you see the bit width of broadcaster operands in different layers. And you see that we can actually heterogeneously quantize the model to improve performance. But more importantly here is that we can manage to move in-memory operands from the baseline 16-bit to 8 bits almost everywhere. So we actually leverage word-level parallelism and ultimately improve performance. Indeed, we measure 55% of performance improvement with respect to that considered baseline. Let me now compare the overall approach with the state-of-the-art alternative. So we have a cycle-accurate simulator to measure performance, as well as a C++ inference simulator to retrieve more accurate accuracy evaluations, because it implements real fixed-point arithmetic. So we consider three different solutions. One is our proposed approach, where the compute memory has an additional register to prevent overflow. Another technique that does not employ this additional register is saturation. So every time that you see an overflow, you can saturate to the maximum or to the minimum value. Another alternative that in this case prevents overflows is by restricting the bit width of in-memory operands so that you ensure that by construction you don't have overflows in that 16-bit register. So these are the results. This plot is just showing you that we can actually leverage multiple subarrays to improve performance. This plot instead is comparing our results with the two baselines. So we observe that we are much faster than the 8-bit IMOS alternative because we can exploit word-level parallelism, but we are slightly slower than saturation because we consider saturate operations being immediate. So we don't account for an additional clock cycle to perform saturations. But in terms of accuracy, this is what we get. So we have comparable accuracy with respect to 8-bit IMOS, because in the end, we both prevent overflows. But saturation cannot really be a solution because it has a dramatic effect on accuracy. So to conclude, we actually propose a scaling of input and output operands to prevent overflows in multiplication, and the hardware design based on compute memory that allows us to prevent overflows in dot products. And we also propose a CNN quantization scheme that allows to improve performance. Then we also combine all these elements together in a holistic hardware software co-design approach to improve performance when executing these models in the designed overflow-free memories. Thank you. Thank you. Yeah, I can take questions.
Thank you, Flavio.
Thank you.
Any questions? You used a layer-wise non-backtracking approach to quantization, which could potentially result in a suboptimal solution.
Yes.
In practice, does it, or is it benign? What were your findings on that?
Okay, so I guess that it should be clear that to determine the best solution in terms of quantization bit width in each layer has a complexity which is exponentially with the number of layers, right? Because you cannot know in advance which is the best configuration that maximizes that. There can be other approaches for sure. So we actually followed a greedy approach just to minimize the impact of this methodology. So we also have, it's dominated by retraining basically. So all of the execution time for the quantization strategy is just retraining. But again, in our case, it's linear with the number of layers because for each layer we determine different bit width and we just retrain for that. Every time that we find that a certain quantization level for certain operands in a certain layer doesn't work, I mean, it doesn't meet the constraint, we just discard it. And in the next iteration, we not consider that. So it's linear in the number of layers. More layers you have, more complex you have. But at least it's not kind of much more complex than that. But again, I agree that better solutions can be found in this exploration.
What I was trying to figure out was, is it a good thing for other people to look at, or did it look like it already
yeah. I mean, you mean in different contexts, not compute memories.
Meaning a more sophisticated optimization strategy when it comes to considering the flows.
Yeah, I mean, for sure, this is, let's say, a proposal we done based on the compute memory we design. So the bitwidth level that we employ is that. Of course, you can stress more that that element in the co-design we have to maximize performance, but we didn't investigate it so deeply that part.
Thank you.
You're welcome. Yeah, maybe later.
So, hi, I'm Christian Dietrich from Hamburg University of Technology, and I wanted to ask, I'm still missing a feeling. You need more space on your die for the circuits in memory and near memory.
Yes.
Can you give me a feeling how that relates? How many general purpose CPUs would I get when I have one megabyte? So,
what do you mean with CPUs? Why CPUs?
so if I trade in the area that you propose to use in memory to have a general purpose, can you give me an idea?
In terms of CPUs, it depends on the CPU, I would say, but I can tell you that the overhead that we have for the whole thing is actually 10% in case of in-memory computing and 12% around in case of near memory, with respect to the 2 kilobytes subarray. So it's not so much. Consider also that we have multiple subarrays, so you have that overhead of 10% in all subarray, but having multiple subarrays in general increases the total overhead in terms of area you have, right? But it also allows you to exploit parallelism over multiple subarrays, right? So you can improve performance without requiring extra CPUs to do the work for that. I think there was a question here, but also there. So you can maybe both, not forget about.
Thank you for your nice talk. My
you.
question would be, I understand you need low overhead in terms of hardware area by doing bit serial operations in memory or close to memory. But can you say something about, in comparison to other throughputs of inference per second, where's your operating points of this in memory or near memory computing with respect to other approaches?
Yes, so in general, this is not the focus of this paper. So we really, I mean, the short answer is we didn't investigate a comparison among different hardware designs. So we haven't done a comparison with the CPUs or things like that. We know for sure that if you consider quantized data, so very low bit with operands, in-memory computing and near-memory computing allows you to get maybe not, for sure, not the best throughput you can imagine, but for sure the best throughput per watt.
All right.
While if you instead focus on something different, like, I don't know, floating point, you need for sure floating point precision in your application, probably the throughput per watt is better if you consider GPUs. But
thank you.
Yeah, okay.
Last question on the word then.
Okay, thank you. I'm Henri Perchal from CA in Grenoble. Maybe it's a related question. Could you explain a little bit how you interact with, because you need a CPU to activate your memory computing? What is the basic idea?
Yes, again, that was not the focus, but no, but I can answer also that. So in practice, this is the acceleration part that you can do in the compute memory. Of course, there should be a control around. So the control can be anything. We also know that the more more overhead you have in your logic to implement fancy stuff to perform computation, the more control you need on the other side. So in this from this perspective, we actually try to minimize the overhead. So you see, the multiplication, for example, is not we don't have a real multiplier. We are just combining very basic operations so that it can also minimize the logic that you need to control the whole stuff. But again, we just focus on the acceleration of compute memory.
Thank you, Flavio.
Thanks to you.